conventional current and potential differences in circuits, and the behavior of ohmic resistors and capacitors. Section 2, we're going to discuss charge conservation and energy conservation in series circuits in the following section. So, our first prediction is that I is equal to V over R, which is going to be equal to 3 volts over 147 ohms, and that's going to be equal to 0.02 amps. So let's see if these predictions are right, and let's see what the ammeter reads when it's inserted backwards. Now, one of the ammeters has been replaced with a voltmeter. We want to describe and explain the readings on the voltmeter and the ammeter. The voltmeter reads the potential difference within the circuit, which is 3 volts. The ammeter now reads 0 amps since the connection has been broken. And you can see that on the right. The current circuit on the right has 0.02 amps. Now you're going to discuss the potential difference between A and B, which is 3 volts, B and C, which is 0 volts, C and D, which is negative 0.959 volts, D and E, which is 0 volts, E and F, which is negative 2.041 volts, F and G, which is 0 volts, G and H, which is 0 volts, and H and A, which is also 0 volts. So we've labeled the points between which we will be calculating the electric potential. And we're going to focus mainly on 5 and 7. So the potential differences between the locations shown in the previous slide all add up to a value of 0 volts. So why doesn't the ammeter reading change with the attachment of the voltmeter? The ammeter reading is 0.02 amps across a 100 ohm resistor. So the slopes, so first let's discuss the graph. The lines on the graph on the right side are based on the values of the potential differences from the previous slide at 0 ohms, and the resistance of the ammeter is also 0 ohms. Now we are moving on to section 3. In section 3, we are going to discuss our RC circuits. So the ammeter now records a value of 0.06 amps. So now we have to consider the resistor of 100 ohms in terms of a parallel circuit. So we'll have a minuscule effect on the current. You would now solve for the current using 3 volts as the voltage and the resistance as 47 ohms. In the first circuit, we will be using a 9-volt battery, a 0.2 farad capacitor, and a 10 ohm light bulb. The light bulb is initially very bright until the capacitor is charged, after which the bulb dims quickly. After disconnecting the battery and connecting the battery directly to the 10 ohm bulb, the bulb lights up and begins to dim again due to the capacitor running out of charge to light up this bulb. In this circuit, we use a 30 ohm light bulb, a 0.2 farad capacitor, and a 9-volt battery, and recorded how the voltage changed from 0 to 20 seconds. I used the setup and the simulation in the previous slide and recorded the voltage and the time at different times ranging from 0 to 20 seconds. There would be more resistance if we did this with a real ammeter, and the simulation does not account for that and provides a current in the most ideal situation. So the ideal model would take longer to charge a real capacitor. The model in the simulation shows the most ideal case of using a capacitor.